Tonight, we're going to explore something terrifying. Imagine you somehow made it to the surface of Venus. You're standing on the ground of another world. But here's the thing nobody tells you. You can't leave. Not because you don't have a rocket, not because you don't have fuel, but because Venus itself won't let you go. The atmosphere above you is so thick, so heavy, so unbelievably dense that it behaves more like an ocean than a sky. The heat is melting your spacecraft. The pressure is crushing it. And the clouds above you, the ones that look like they might offer relief, they're filled with acid. Venus isn't just hostile, it's a trap. A planetary prison designed by physics itself. And by the end of tonight, you're going to understand exactly why. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you know. Venus. You've probably heard it called Earth's twin, and on paper, that comparison makes sense. Venus is almost the same size as Earth. Its diameter is about 12,104 kilometers, compared to Earth's 12,742. That's roughly 95% of Earth's width. The two planets have similar masses, similar densities, and they formed from the same cloud of gas and dust about 4.6 billion years ago in the same region of the young solar system. If you were an alien astronomer looking at our solar system from a distant star, you might assume these two planets were nearly identical. Two rocky worlds of similar size orbiting in the inner region of a yellow dwarf star. You might even guess they had similar conditions on their surfaces. Similar temperatures, similar atmospheres, maybe even similar chances of hosting life. You would be catastrophically wrong, because Venus is not Earth's twin. It's Earth's nightmare. It's what happens when a planet that starts with almost every advantage slowly, irreversibly turns against itself. And what it has become is something so hostile, so extreme, so fundamentally opposed to anything we would recognize as survivable that even our most advanced technology can barely touch its surface before being destroyed. Venus isn't just a difficult place, it's the most hostile planetary surface in the inner solar system. More hostile than Mercury, which has no atmosphere and swings between extreme heat and cold. More hostile than Mars, which is freezing and has almost no atmosphere, but at least lets our rovers drive around for years. Venus is in a category of its own, and to understand why it would never let you escape, you first have to understand what it would do to you the moment you arrived. Let's talk about temperature. The surface of Venus has an average temperature of about 465 degrees Celsius. That's roughly 870 degrees Fahrenheit. Let me put that number in context because it sounds like just another big number, but it's far more extreme than most people realize. Lead melts at 300 to 27 degrees Celsius. Zinc melts at 419 degrees Celsius. The surface of Venus is hot enough to melt both of these metals. If you placed a bar of lead on the surface of Venus, it wouldn't just get warm. It would become a puddle. Tin, which melts at 232 degrees Celsius, would flow like water. Even some aluminum alloys would begin to soften and deform at these temperatures depending on their composition. This isn't the kind of heat you experience in a desert on Earth, where temperatures might reach 50 or 55 degrees Celsius. The surface of Venus is nearly twice as hot as your kitchen oven at its highest setting. It's closer to the temperature inside a kiln used to fire ceramics or smelt certain metals, this is industrial heat. And on Venus, this isn't some localized hotspot near a volcano or a thermal vent. This is everywhere. The entire surface. Every square meter of the planet. North Pole, South Pole, equator, mountaintops, valley floors, dayside, nightside. It doesn't matter. The temperature is essentially the same everywhere on Venus, and it never changes. There are no seasons. There's no meaningful temperature difference between day and night. The atmosphere is so thick and so efficient at trapping and distributing heat that the surface temperature remains locked at around 465 degrees Celsius all the time, everywhere. This is important. On Earth, you can escape heat by going somewhere cooler. You can climb a mountain, travel toward the poles, wait for nightfall. On Venus, there is no escape. No cooler region to reach, no nighttime relief, no altitude that brings the temperature down quickly enough to matter within reach of the surface. The heat is uniform, constant, and inescapable. You are cooked from the moment you arrive, and you will continue to be cooked no matter where you go or how long you wait. Now let's talk about why Venus is this hot. Because the answer reveals something fundamental about the planet's nature. Venus is not closer to the Sun than Mercury. Mercury orbits at an average distance of about 58 million kilometers from the Sun. Venus orbits at about 108 million kilometers. Mercury is almost twice as close to the Sun as Venus is, and yet Mercury's average surface temperature is only about 167 degrees Celsius. Venus, despite being farther from the Sun, is nearly 3 times hotter. How is that possible? The answer is the atmosphere. Mercury has essentially no atmosphere. Whatever heat it receives from the Sun radiates back into space freely. The side facing the Sun gets blisteringly hot, up to about 430 degrees Celsius. But the side facing away plunges to minus 180 degrees Celsius. There's nothing to trap the heat, nothing to distribute it, nothing to prevent it from escaping. Venus is the opposite. Venus has an atmosphere so thick, so massive, and so effective at trapping heat that it has created the most extreme greenhouse effect in the solar system. The atmosphere of Venus is about 96.5% carbon dioxide. Carbon dioxide is a greenhouse gas, meaning it allows sunlight to pass through, but absorbs and re-emits infrared radiation, the heat that the surface tries to radiate back into space. On Earth, carbon dioxide makes up only about 0.04% of the atmosphere, and even that small amount contributes significantly to our planet's greenhouse effect, keeping Earth warm enough for liquid water. On Venus, the atmosphere is almost entirely carbon dioxide. The greenhouse effect isn't subtle, it's overwhelming. Sunlight passes through the upper atmosphere, reaches the surface, heats the ground, and the ground tries to radiate that heat back into space as infrared radiation. But the massive blanket of carbon dioxide absorbs that radiation and sends much of it back down. The surface heats up more, it radiates more intensely. The atmosphere absorbs more. The cycle continues until an equilibrium is reached. And on Venus, that equilibrium is 465 degrees Celsius. This is what scientists call a runaway greenhouse effect. It's a feedback loop that spiraled out of control billions of years ago and never stopped. Some planetary scientists believe Venus may have once had liquid water on its surface. Models suggest that early Venus, billions of years ago, might have had oceans and a much more temperate climate. But as the young sun gradually increased in luminosity over hundreds of millions of years, Venus's surface temperature began to rise. Water began to evaporate. Water vapor is itself a greenhouse gas, so more water in the atmosphere trapped more heat, which evaporated more. Water, which trapped more heat. At some point, the process became self-reinforcing. The oceans boiled. The water vapor in the upper atmosphere was broken apart by ultraviolet radiation from the sun, a process called photodissociation. The hydrogen escaped into space. The oxygen was absorbed into surface rocks. The water was gone, permanently. And without water to dissolve carbon dioxide and lock it into rocks through weathering, the carbon dioxide that was released by volcanic activity accumulated in the atmosphere. On Earth, the carbon cycle moves carbon dioxide from the atmosphere into the oceans and into rocks, keeping levels relatively low. On Venus, with no oceans and no carbon cycle, carbon dioxide just kept building up. The atmosphere grew thicker. The greenhouse effect grew stronger. The temperature climbed higher. And here we are, 465 degrees Celsius. No water, no escape. Now let's talk about pressure. Because the temperature alone isn't what makes Venus truly horrifying. It's the combination of temperature and pressure that turns the surface into something almost unimaginable. The atmospheric pressure on the surface of Venus is about 92 times the atmospheric pressure at sea level on Earth. On Earth, the atmosphere presses down on you with a force of about 101,325 pascals, or roughly 1 atmosphere. You don't notice it because your body evolved to function at this pressure. Your lungs, your blood vessels, your cells are all designed to operate with 1 atmosphere of pressure pushing on them from all sides. On Venus, the pressure is 92 atmospheres. That is equivalent to the pressure you would experience if you dove to a depth of about 920 meters in Earth's ocean. Almost a full kilometer underwater. No human has ever survived at that depth without a specialized deep-sea submersible. The deepest any human has ever gone in a submersible is about 11,000 meters in the Mariana Trench, but the vessels designed for those depths are built like tanks. Thick titanium shells designed to withstand crushing forces from every direction. At 920 meters depth, the pressure would crush an unprotected human body. Your lungs would collapse. The air spaces in your sinuses and inner ears would implode. Your ribcage would deform. Death would be immediate and violent. That's the pressure waiting for you on the surface of Venus. Not underwater, not in some extreme deep-sea environment. Just standing on the ground in the open air. Except it's not really air. It's a supercritical fluid of carbon dioxide so dense and so compressed that it behaves more like a liquid than a gas. This is a crucial point that most people miss when they think about Venus. At the temperatures and pressures found near Venus's surface, carbon dioxide doesn't behave the way you'd expect a gas to behave. At 92 atmospheres and 465 degrees Celsius, carbon dioxide is above its critical point. This means it exists in a state that's neither truly gas nor truly liquid, but something in between, a supercritical fluid. Supercritical fluids have properties of both liquids and gases. They can diffuse through materials like a gas, but they have densities closer to a liquid. The density of Venus's atmosphere at the surface is about 65 kilograms per cubic meter. For comparison, the density of Earth's atmosphere at sea level is about 1.2 kilograms per cubic meter. Venus's surface atmosphere is roughly 54 times denser than the air you're breathing right now. Water has a density of 1,000 kilograms per cubic meter. So Venus's atmosphere isn't as dense as water, but it's dense enough that you would feel significant buoyancy if you tried to move through it. Objects on Venus's surface experience an upward buoyant force from the thick atmosphere. A human body would feel noticeably lighter on Venus, not because gravity is weaker. Venus's surface gravity is about 90% of Earth's, but because the dense atmosphere is pushing upward on everything immersed in it, just like water pushes up on objects submerged in a pool. Walking on the surface of Venus, if you could somehow survive, would feel like wading through a thick, invisible fluid. The wind, even a gentle breeze of just a few kilometers per hour, would push against you with surprising force because the medium carrying that wind is so dense. Even slow winds on Venus carry enormous energy. A wind speed that would feel like a gentle breeze on Earth would feel like a strong current pushing against you on Venus because the atmosphere has so much more mass behind it. This is the environment that the Soviet Union's Venera program sent spacecraft into during the 1970s and 1980s. The Venera missions remain some of the most audacious and impressive achievements in the history of space exploration. Between 1961 and 1984, the Soviet Union launched a series of probes toward Venus. The early missions failed. Venera 3 in 1966 became the first human-made object to reach the surface of another planet, but it was crushed by the atmosphere before it could send back any data. The engineers had dramatically underestimated how extreme conditions on Venus really were. They had designed the probe to withstand pressures of about 25 atmospheres, thinking that would be more than enough. It wasn't even close. The atmosphere crushed it like an empty can. Subsequent missions were redesigned with stronger and stronger pressure vessels. Venera 7 in 1970 became the first spacecraft to successfully transmit data from the surface of another planet. It survived for about 23 minutes on the surface before succumbing to the heat and pressure. Later, Venera missions were built even stronger. Venera 9 in 1975 survived about 53 minutes and transmitted the first photographs from the surface of another planet. The images showed a landscape of flat rocks stretching to the horizon under an orange sky. The lighting was dim, about as bright as an overcast day on Earth, because the thick atmosphere filters and scatters so much sunlight. Venera 13 in 1982 achieved the longest survival time on Venus's surface, lasting about 127 minutes, just over 2 hours. It transmitted color photographs and even analyzed soil samples. The images it sent back showed a surface covered in flat, broken rocks that looked almost like shattered tiles. The sky was a deep orange color, the result of the thick atmosphere filtering out blue light and allowing primarily yellow and red wavelengths to reach the surface. Think about what this means from an engineering standpoint. The Soviet engineers built these probes to be as tough as physically possible. They used titanium pressure vessels. They pre-cooled the interiors before descent so the electronics would start from a lower temperature and last longer before overheating. They designed every component to function at extreme temperatures. They used specialized lubricants and seals rated for hundreds of degrees. And with all of that engineering, with some of the best materials and designs available to a superpowered space program, the absolute best they could achieve was 2 hours and 7 minutes of survival. 2 hours on the surface of a planet. That's not a limitation of ambition or funding. That's a limitation imposed by physics. The heat is so intense and so relentless that it overwhelms any thermal protection system within hours. Electronics fail as temperatures rise beyond their operating limits. Seals degrade, lubricants break down, solder softens, materials expand at different rates, causing joints to crack and fail. The spacecraft doesn't just stop working, it's slowly destroyed, component by component, as the heat of Venus penetrates every barrier and reaches every vulnerable part. No spacecraft has landed on Venus since the Soviet Vega 2 mission in 1985. That's 4 decades. It's not because we lost interest. It's because Venus is so difficult that even with modern technology, designing a lander that can survive long enough to do meaningful science remains one of the greatest engineering challenges in planetary exploration. NASA has proposed a mission concept called Da Vinci, which would send a probe into Venus's atmosphere, and another concept called Veritas, an orbiter, but a long-duration surface mission, something that could survive for days or weeks rather than minutes, remains beyond our current capability. Various concepts have been proposed, including using silicon carbide electronics that can operate at high temperatures, or even a mechanical computer, a clockwork-style device with no electronic components that could theoretically function in Venus's heat for much longer. But none of these have been built and tested on Venus. This is the baseline. This is the starting point. Before you even think about escaping Venus, before you even consider the problem of getting off the surface and back into space, you have to reckon with the fact that simply existing on the surface is a death sentence measured in minutes. Not hours, not days, minutes. Your spacecraft is dying from the moment it touches down. Every second you spend on the surface is a second closer to total system failure. The heat is cooking your electronics. The pressure is stressing your hull. The dense atmosphere is pushing against every surface, every seal, every joint. You're not visiting Venus, you're being consumed by it, and this matters enormously for the escape problem. Because escaping from a planet isn't instantaneous. On Earth, a rocket launch takes minutes of powered flight to reach orbit. The space shuttle's main engines burned for about 8.5 minutes during ascent. A launch from Venus would take longer because the atmosphere is so much thicker and creates so much more drag. You'd need to burn engines for a longer time to fight through all that resistance. And every extra minute your vehicle spends on or near the surface is another minute of thermal destruction. Your rocket engines, your fuel tanks, your guidance systems, your structural components, all of them are being degraded by the heat while you're trying to use them. It's like trying to build a bridge while the bridge is on fire. You're not just fighting gravity. You're not just fighting the atmosphere. You're fighting the clock. Venus is destroying your vehicle in real time, and you have to escape before it finishes the job. This creates a paradox that makes Venus uniquely terrifying among all the worlds in our solar system. To escape from a planet, you need a vehicle capable of generating enormous thrust for a sustained period. That vehicle needs fuel, engines, structural integrity, and functioning guidance systems. All of these things are vulnerable to extreme heat and pressure. And Venus provides the most extreme heat and pressure of any rocky planet surface we know. The very conditions that make you want to escape are the same conditions that are destroying your ability to escape. The planet isn't just holding you down with gravity, it's actively dismantling your means of leaving. On Earth, we take for granted that our rockets work. We fuel them, we light the engines, and they function as designed because Earth's surface conditions are benign. Room temperature, 1 atmosphere of pressure, a thin atmosphere that thins rapidly with altitude. None of these things are true on Venus. On Venus, Your rocket is sitting in an environment that would destroy most industrial equipment within hours. The fuel in your tanks is being heated, which changes its properties and can make it dangerously unstable. The metal structures of your vehicle are being subjected to thermal expansion that can warp and weaken joints. Your engine nozzles, designed to direct superheated exhaust gases, are already immersed in a superheated atmosphere, which changes their performance characteristics. Your guidance electronics, the computers that control the ascent, are being baked. Consider this comparison. On Earth, the temperature difference between the ambient air and a rocket engine's exhaust is enormous. A rocket engine might produce exhaust at 3,000 degrees Celsius, while the surrounding air is perhaps 20 degrees Celsius. That massive temperature difference is part of what makes the engine efficient. On Venus, the surrounding atmosphere is already at 465 degrees Celsius. The temperature difference between the ambient environment and the engine exhaust is smaller. This doesn't prevent the engine from working, but it does affect efficiency, and it means that the entire vehicle is already at a temperature that would cause serious problems for most engineering materials and systems. The Soviet engineers who designed the Venera landers understood all of this. That's why no Venera mission ever attempted to launch anything back off the surface. It wasn't part of the plan. The landers were designed as one-way trips, falling through the atmosphere, landing, collecting data for as long as possible, and then dying. Getting something off Venus's surface and back into space was a problem so far beyond the technology of the 1970s and 80s that it wasn't even seriously considered. And honestly, it's a problem that remains largely unsolved today, decades later, with far more advanced materials and engineering capabilities. So here's where we stand. You're on the surface of Venus. The temperature around you is 465 degrees Celsius, hot enough to melt lead and zinc. The pressure is 92 times what you're used to on Earth, equivalent to being nearly a kilometer underwater. The atmosphere is so dense it behaves like a fluid rather than a gas. Your spacecraft, whatever it is already dying. Its systems are failing one by one as the heat penetrates every thermal barrier. You have minutes, maybe a couple of hours at most, before total failure. And you haven't even started trying to leave. You haven't fired a single engine. You haven't risen a single meter off the ground. You're trapped on the floor of an alien ocean made of superheated carbon dioxide, in a furnace that never turns off, under a sky so thick with gas that it presses down on you with the weight of 900 meters of water. This is the first layer of Venus's trap. Not the atmosphere above you, not the clouds, not the orbital mechanics, just the surface, just existing on this world. The floor of the prison is already lethal, and everything above it, as we're about to discover, is designed to keep you there. Now, let's say you somehow solve the surface problem. You've built a vehicle tough enough to survive the heat and pressure long enough to attempt an ascent. Your engines are functioning. Your fuel hasn't destabilized. Your guidance systems are still online. You're ready to go up. You fire your engines and begin to rise off the surface of Venus. And immediately you encounter the real trap. Because the surface was just the beginning. The atmosphere of Venus is not like the atmosphere of Earth. It's not a thin shell of gas that you punch through quickly on your way to space. It's a massive, dense, suffocating blanket that extends for dozens of kilometers above the surface, and every single meter of altitude you gain is a fight against physics that Earth has never prepared you for. Let me explain what you're actually pushing through. At the surface of Venus, the atmospheric density is about 65 kilograms per cubic meter. That number might not mean much on its own, so let me give you something to compare it to. The density of Earth's atmosphere at sea level is about 1.2 kilograms per cubic meter. So the gas surrounding you on Venus's surface is roughly 54 times denser than the air you breathe every day. But here's another comparison that might make it more visceral. Liquid water has a density of 1,000 kilograms per cubic meter. Venus's surface atmosphere is about 6.5% the density of water. That sounds like a small percentage until you realize what it means in practical terms. You're not flying through air. You're pushing through a medium that has a meaningful fraction of the density of water. If you've ever tried to run in a swimming pool, wading through water up to your waist, you know how much resistance a dense medium creates. Every movement is slower, harder, more exhausting. Now imagine trying to fly a rocket through a medium that's somewhere between air and water in density. Not as thick as water, but unimaginably thicker than any atmosphere you've ever experienced. That's what the first few kilometers above Venus's surface are like. Aerodynamic drag is the force that resists an object's motion through a fluid. On Earth, drag is something aerospace engineers deal with constantly. It's why airplanes have streamlined shapes. It's why rockets are designed as narrow cylinders rather than broad, flat surfaces. Drag depends on several factors: the speed of the object, the density of the medium it's moving through, the object's cross-sectional area, and its shape. The critical factor here is density. Drag force increases linearly with the density of the medium. If you double the density of the fluid, you double the drag. If you increase the density by a factor of 54, which is approximately the ratio between Venus's surface atmosphere and Earth's sea level atmosphere, you increase the drag by a factor of 54. That means a rocket ascending from Venus's surface at the same speed as a rocket ascending from Earth would experience roughly 54 times more atmospheric drag, 54 times more resistance pushing it back down, 54 times more force that the engines have to overcome just to keep moving upward. On Earth, atmospheric drag is a real concern during rocket launches, but it's manageable. Rockets throttle back during the period of maximum aerodynamic pressure, a point engineers call max Q, typically occurring around 10 to 15 kilometers altitude. After max Q, the atmosphere thins rapidly, drag decreases, and the rocket can accelerate more aggressively. On Earth, the atmosphere thins to about 1% of its surface density by around 30 kilometers altitude. By 50 kilometers, you're essentially in a vacuum for practical purposes. The total amount of atmosphere you have to push through is relatively modest. On Venus, the situation is catastrophically different. The atmosphere doesn't just start denser, it stays denser for much longer as you ascend. On Earth, atmospheric pressure drops by half, roughly, every 5.5 kilometers. On Venus, because the atmosphere is so massive and because the gravitational acceleration is similar to Earth's, the pressure also decreases with altitude, but from a much higher starting point. At 10 kilometers above Venus's surface, the atmospheric pressure is still about 47 atmospheres. That's nearly half the surface pressure, and it's still 47 times the pressure at sea level on Earth. At 20 kilometers altitude, the pressure is still about 22 atmospheres. At 30 kilometers, about 10 atmospheres. Even at 40 kilometers above the surface, the pressure is about 3.5 atmospheres. Still more than 3 times the atmospheric pressure at the bottom of the Grand Canyon on Earth. Let me put this in perspective with Earth. At 40 kilometers altitude on Earth, you're in the stratosphere. The atmosphere is so thin that the pressure is only about 0.3% of sea level pressure. If you were at 40 kilometers on Earth, you'd essentially be in space for any practical human purpose. On Venus, at that same altitude, the atmosphere is still denser than Earth's surface atmosphere. You've climbed 40 kilometers, burning fuel the entire time, fighting drag and gravity, and the atmosphere around you is still thicker than anything you would experience anywhere on Earth's surface. The air outside your vehicle is still pressing harder on your hull than the atmosphere at the bottom of the deepest valley on Earth. This means your vehicle has to fight through a meaningful atmosphere for far longer than it would on Earth. On Earth, the hard part of atmospheric flight lasts maybe the first 30 kilometers. After that, you're mostly in vacuum and can accelerate freely. On Venus, the hard part lasts for at least 50 or 60 kilometers. That's 50 or 60 kilometers of dense atmosphere creating drag on your vehicle, slowing it down, forcing the engines to burn harder and longer. And every second of engine burn consumes fuel. Fuel that has mass. Mass that the rocket has to carry, which makes it heavier, which means it needs more thrust to accelerate, which means it needs more fuel. This is the tyranny of the rocket equation, and Venus makes it dramatically worse than Earth does. The temperature profile during ascent matters enormously too. On Earth, temperature generally decreases as you go up through the troposphere, dropping by about 6.5 degrees Celsius for every kilometer of altitude gained. By the time you reach 10 kilometers, the temperature has dropped to about minus 50 degrees Celsius. Your rocket actually cools down as it ascends, which is helpful for thermal management. On Venus, the temperature does decrease with altitude, but it starts so high and drops so slowly that it remains lethal for a punishing stretch. At 10 kilometers above the surface, the temperature is still about 400 degrees Celsius. At 20 kilometers, it's about 330 degrees Celsius. At 30 kilometers, about 220 degrees Celsius. At 40 kilometers, about 140 degrees Celsius. Even at 50 kilometers altitude, the temperature is still around 75 degrees Celsius, which is about 167 degrees Fahrenheit. That's hot enough to cause severe burns to human skin instantly. So for the first 50 kilometers of your ascent, which at vehicle speeds of a few hundred meters per second could take several minutes of continuous engine burn, your vehicle is immersed in an atmosphere that is simultaneously crushingly dense, blisteringly hot, and creating enormous drag. Your thermal protection systems, which were already stressed from sitting on the surface, are continuing to absorb heat. Your engine components are operating in an environment far hotter than the ambient conditions they'd face during a launch from Earth. Your fuel tanks are being heated externally, which raises the temperature and pressure of the fuel inside, which can affect engine performance and create safety risks. Let me walk you through what this ascent would actually look like, step by step, so you can appreciate just how different it is from anything we do on Earth. On Earth, a rocket sitting on the launch pad is surrounded by air at roughly 20 degrees Celsius and 1 atmosphere of pressure. When the engines ignite, the rocket begins to rise. It accelerates through the atmosphere, fighting gravity and drag. Within about 2 minutes, it's traveling at several thousand kilometers per hour and has risen to about 40 or 50 kilometers, where the atmosphere is negligibly thin. The whole trip through the meaningful atmosphere takes maybe 2 to 3 minutes. The thermal environment outside the vehicle goes from warm to cold very quickly. The structural loads from aerodynamic pressure peak around 10 to 15 kilometers, and then drop rapidly. It's challenging, but is over quickly. On Venus, your rocket is sitting in an atmosphere at 465 degrees Celsius and 92 atmospheres of pressure. The moment you ignite your engines, you're already fighting against a medium 54 times denser than anything an Earth rocket ever faces. Your vehicle begins to rise, but sluggishly, because the drag is immense. Every square meter of your vehicle's surface that faces the direction of travel is being pushed back by a wall of dense, hot gas. To achieve the same acceleration that an Earth rocket gets in thin air, your Venus rocket needs dramatically more thrust. More thrust means bigger engines. Bigger engines mean more mass. More mass means even more thrust needed, which means more fuel, which means more mass. The cycle compounds on itself. As you climb, the atmosphere does thin, but agonizingly slowly. After 10 kilometers of ascent, burning engines the entire time, consuming fuel at a ferocious rate, the atmosphere is still 47 times denser than Earth's surface air. The temperature has dropped, but only to about 400 degrees Celsius. Your vehicle is still being pressure cooked and is still fighting through what amounts to a wall of gas. After 20 kilometers, you're at 22 atmospheres and 330 degrees. The drag has decreased, but is still many times worse than anything encountered during an Earth launch. After 30 kilometers, 10 atmospheres and 220 degrees Celsius. You've been burning engines for a significant stretch now, consuming enormous amounts of fuel, and you're still in an atmosphere thicker than any atmosphere on Earth. Compare this to what a rocket launching from Earth experiences at 30 kilometers altitude. On Earth at 30 kilometers, the atmospheric pressure is about 1.2% of surface pressure. The air is so thin, it's barely there. An Earth rocket at 30 kilometers is essentially in vacuum and can accelerate freely toward orbital velocity with almost no drag. A Venus rocket at 30 kilometers is in an atmosphere that's still 10 times denser than Earth's surface air. The difference is staggering. This atmospheric density doesn't just create drag, it also affects how rocket engines perform. Rocket engines work by expelling exhaust gas at high velocity out of a nozzle. The efficiency of this process depends partly on the pressure difference between the exhaust gas and the surrounding atmosphere. At sea level on Earth, the ambient pressure is 1 atmosphere, and rocket nozzles are designed to work efficiently at this pressure. As the rocket climbs and the atmospheric pressure drops, the exhaust can expand more, and nozzle efficiency changes. This is why some rockets use different engines or different nozzle configurations for different stages of flight. First stage engines are optimized for sea level pressure. Upper stage engines are optimized for vacuum. On Venus, the ambient pressure at the surface is 92 atmospheres. A rocket nozzle designed to operate at 1 atmosphere, like the ones we use on Earth, would be grossly inefficient at 92 atmospheres. The exhaust would be unable to expand properly. The engine would produce significantly less thrust per unit of fuel consumed. To operate efficiently at Venus surface pressures, you'd need a completely different nozzle design, one with a much smaller exit area relative to the throat. But that nozzle would become increasingly inefficient as you climbed, and the pressure dropped. By the time you reached regions where the pressure was closer to Earth-like levels, your surface-optimized nozzle would be performing poorly. This is why engineers talk about using stage systems for a Venus ascent vehicle. You might need one engine configuration optimized for the crushing pressures near the surface, and a different configuration optimized for the thinner atmosphere at higher altitudes. But each additional engine system adds mass. Mass that needs fuel. Fuel that adds more mass. The problem spirals. Let me talk about the energy budget, because this is where the mathematics becomes truly punishing. The amount of energy required to lift a vehicle from a planet's surface to orbit depends on several factors. The planet's gravity, the depth and density of its atmosphere, and the orbital velocity required. Venus's surface gravity is about 8.87 meters per second squared, compared to Earth's 9.81. So gravity is slightly less on Venus, about 90% of Earth's. That's the one small mercy Venus offers. You need slightly less energy to overcome gravity alone. But this small advantage is completely overwhelmed by the atmospheric penalty. The energy required to push through Venus's atmosphere during ascent is enormously greater than the energy required on Earth. Aerospace engineers quantify this using a concept called delta V, which represents the total change in velocity a vehicle needs to achieve to complete a mission. For a launch from Earth's surface to low Earth orbit, the required delta V is about 9.4 kilometers per second. This accounts for the orbital velocity of roughly 7.8 kilometers per second, plus additional velocity needed to overcome gravity losses during the ascent and aerodynamic drag losses from pushing through the atmosphere. On Earth, drag losses account for roughly 0.3 to 0.5 kilometers per second of the total delta V budget, depending on the vehicle's design and trajectory. It's a meaningful contribution, but not dominant. On Venus, the drag losses would be vastly greater. Detailed engineering studies have estimated that the delta V required for a launch from Venus's surface to low Venus orbit would be significantly higher than the equivalent on Earth, primarily because of the enormous atmospheric drag. The total delta V has been estimated at 11 to 12 kilometers per second or more, depending on vehicle design and trajectory. The extra 2 to 3 kilometers per second compared to Earth might not sound like much, but in rocketry, small increases in delta V requirements lead to exponential increases in the amount of fuel needed. This is because of the Tsiolkovsky rocket equation, the fundamental equation that governs all rocket propulsion. The rocket equation says that the ratio of a rocket's initial mass, including fuel to its final mass after the fuel is burned, increases exponentially with the required delta V. If you need to increase your delta V by even a small amount, the fuel requirement doesn't just go up proportionally, it goes up exponentially. This is what aerospace engineers mean when they talk about the tyranny of the rocket equation. Every additional kilogram of fuel you add to the vehicle makes it heavier, which means you need more fuel to accelerate that additional mass, which makes it heavier still. On Earth, this exponential relationship is already punishing. A typical rocket at launch is about 90% fuel by mass. The actual payload, the thing you're trying to get to orbit, is only about 2 to 4% of the total launch mass. The rest is fuel, and the structure needed to hold the fuel. On Venus, with higher delta V requirements, the fuel fraction would be even higher. You'd need a vehicle that is even more dominated by fuel. And here's the thing that makes it truly nightmarish. That fuel has to survive the surface conditions of Venus. It has to remain stable at 465 degrees Celsius and 92 atmospheres of pressure. Many common rocket propellants would be unstable or would react uncontrollably under these conditions. The fuel and oxidizer would need to be specially selected for Venus conditions, and the options are limited. Some propellant combinations that work perfectly on Earth might be unusable on Venus because the ambient temperature is so high that the propellants would react prematurely or degrade. Several studies have looked at what propellant combinations might work for a Venus ascent vehicle. One option that's being considered is hydrazine-based propellants, but these have handling and stability concerns at high temperatures. Another option is solid rocket propellants, which can be more thermally stable, but solid rockets are harder to control and typically have lower specific impulse, meaning they're less fuel efficient. The thermal management of the propellants during the surface stay and early ascent is itself a major engineering challenge. You might need to insulate the fuel tanks extensively, or use propellants that are inherently stable at high temperatures, even if they're less efficient than what you'd choose on Earth. There's another problem that doesn't get talked about as often but is equally important. The structural loads on a vehicle ascending through Venus's atmosphere would be immense. On Earth, the maximum dynamic pressure during ascent, that max Q I mentioned earlier, typically peaks at about 30 to 40 kilonewtons per square meter. This is the maximum aerodynamic stress the vehicle experiences, and rockets are designed to handle it. On Venus, because the atmospheric density is so much higher, max Q would occur at a lower altitude and at a lower velocity, but it would be much more intense. The vehicle would need to be structurally stronger to handle these loads. Stronger structures mean more mass. More mass means more fuel. More fuel means more mass. The spiral continues. The vehicle would also need to be designed for extreme heating during ascent. On Earth, aerodynamic heating during rocket ascent is a factor, but not a primary concern for the structure. The speeds are high, but the atmosphere is thin enough that the heating is manageable. On Venus, the combination of high atmospheric density and the need for significant velocity through that dense atmosphere creates a severe heating environment. The vehicle's surface would be subjected to convective heating from the hot, dense atmosphere rushing past it at high speed. This is on top of the ambient temperature of the atmosphere itself. So you have a vehicle that's already at hundreds of degrees Celsius from the surface environment, and now aerodynamic heating is adding even more thermal energy on top of that. Heat shields, or thermal protection systems, would need to handle both the ambient heat and the aerodynamic heating simultaneously. Let me add one more factor that makes the Venus ascent problem even worse. Wind. Venus's lower atmosphere, below about 10 kilometers, has relatively slow winds of just a few kilometers per hour. But as you climb, the wind speeds increase. By 40 to 50 kilometers altitude, the atmosphere is moving at speeds of roughly 100 to 150 kilometers per hour. Higher up, in the cloud layers around 60 to 70 kilometers, wind speeds reach 300 to 360 kilometers per hour. These winds circle the planet much faster than the planet itself rotates, a phenomenon called atmospheric super-rotation. Venus rotates extremely slowly, taking about 243 Earth days to complete one rotation. But its upper atmosphere circles the planet in just about 4 Earth days. This means the upper atmosphere is moving roughly 60 times faster than the planet's surface. For an ascending vehicle, these winds create additional aerodynamic challenges. The vehicle doesn't just need to go straight up. It encounters winds that change speed and direction with altitude. These wind shears create forces on the vehicle that the guidance system must compensate for. On Earth, Wind shear is a concern during rocket launches, but the forces involved are relatively modest because the atmosphere is thin. On Venus, wind shear in a dense atmosphere creates much larger forces. A sudden change in wind speed of 50 kilometers per hour at an altitude where the atmospheric density is still several times Earth's surface density would create structural loads that could damage or destroy a vehicle not designed to handle them. And all of this has to work autonomously. Because of the distance between Venus and Earth, there's a communication delay of between 4 and 24 minutes, depending on orbital positions. You can't pilot a Venus ascent vehicle in real time from Earth. You can't react to problems as they happen. The vehicle has to be pre-programmed to handle every contingency on its own. If something goes wrong during the ascent, if a gust of wind pushes the vehicle off course, if an engine underperforms, if a thermal seal fails, the vehicle has to detect the problem and respond correctly without any human input. And its guidance computers have to function in an environment that has been cooking them since the moment the vehicle landed. So let me paint the full picture of what it takes to ascend through the lower atmosphere of Venus. You ignite your engines on the surface in conditions equivalent to a kilometer underwater and hot enough to melt lead. Your engines have to produce enormous thrust to overcome both gravity and the drag of an atmosphere 54 times denser than Earth's. Your nozzles are operating inefficiently because the ambient pressure is crushing the exhaust. Your vehicle pushes upward through what feels more like a fluid than a gas, fighting drag forces that no Earth rocket has ever experienced. Every second, you're burning through fuel at a furious rate. The atmosphere around you is so hot that your thermal protection is being overwhelmed. Your structure is expanding and deforming. Your electronics are creeping toward failure temperatures. As you climb, the atmosphere thins, but slowly, painfully slowly. After 10 kilometers of powered ascent, conditions outside are still worse than anything found on Earth's surface. After 20 kilometers, the pressure has dropped to roughly the equivalent of Earth's surface. But the temperature is still over 300 degrees Celsius, and the density is still enormous by Earth standards. After 30 kilometers, you're finally in an environment that's merely terrible, rather than utterly impossible. The pressure is about 10 atmospheres, the temperature about 220 degrees. You've been burning engines continuously for far longer than an Earth rocket burns during its first stage, and you've consumed a massive fraction of your fuel. At around 40 to 50 kilometers, the atmosphere begins to approach conditions that a human might consider almost tolerable. The temperature drops below 100 degrees Celsius around 55 kilometers. The pressure drops to levels comparable to Earth's surface atmosphere. The density decreases to something resembling actual air rather than a thick fluid. Your vehicle can finally start to accelerate more efficiently. The drag has decreased enough that your engines are no longer fighting a wall of gas. But you've spent an enormous amount of fuel getting here. Your vehicle is lighter now because so much fuel has been burned, but it's also structurally compromised by the thermal stresses it has endured. And you still haven't reached the cloud layers. Those begin at about 48 kilometers altitude, and they bring a completely new set of problems. But before we get to the clouds, let me make sure you understand the fundamental point of everything I've just described. The lower atmosphere of Venus is not just an inconvenience for ascent. It is a physical barrier of extraordinary magnitude. It is a wall of dense, hot, high-pressure gas that extends for dozens of kilometers above the surface and requires an enormous expenditure of energy to push through. The energy cost of ascending through this atmosphere is so high that it fundamentally changes the engineering requirements for any vehicle attempting to leave Venus's surface. A vehicle that could easily reach orbit if launched from Earth would be hopelessly inadequate on Venus. The atmosphere adds so much drag, so much thermal stress, and so much additional delta-V requirement that the entire vehicle has to be reimagined from the ground up. This is what makes Venus fundamentally different from every other destination in the inner solar system. Mars has an atmosphere, but it's so thin that it barely matters during ascent. Landing on Mars is tricky because the atmosphere is thick enough to create heating but too thin to slow you down effectively. So you need both heat shields and rockets. But launching from Mars is relatively easy. The atmospheric drag is negligible, the gravity is only about 38% of Earth's, and the delta V to orbit is only about 3.8 kilometers per second. A relatively small rocket could do it. The moon has no atmosphere at all. Launching from the moon is purely a matter of overcoming gravity, and the moon's gravity is only about 17% of Earth's. The delta V to lunar orbit is about 1.8 kilometers per second. A modest ascent stage can do the job, as Apollo demonstrated. Even Earth, with its substantial atmosphere, is manageable. The atmosphere creates drag, but it thins rapidly. The period of maximum aerodynamic stress lasts only about a minute during ascent. Rockets punch through the thick part quickly, and then they're free. Venus is in a different category entirely. The atmosphere doesn't just slow you down for a minute or two. It fights you for tens of kilometers. It doesn't just create aerodynamic drag. It creates a thermal environment that actively destroys your vehicle. It doesn't just require a little extra fuel. It requires a fundamentally larger and more robust vehicle to carry enough propellant and muscle through all that dense gas. The lower atmosphere of Venus is not a sky. It's an ocean of carbon dioxide so hot and so dense that pushing through it from bottom to top is more comparable to a submarine trying to surface from great depth than an airplane trying to climb through weather. And you are somewhere near the bottom, trying to rise through the heaviest, hottest, most unforgiving layer of gas on any rocky planet in the solar system. The surface was the floor of the trap. The lower atmosphere is the wall. It surrounds you on all sides, extends far above you, and resists every attempt to push through it with a force that is relentless, enormous, and unlike anything we have ever faced in all of human spaceflight. Let's say you've made it. Against all odds, your vehicle has survived the surface. It fired its engines in an environment hot enough to melt lead, pushed through an atmosphere dense enough to feel like a fluid, burned through enormous quantities of fuel-fighting drag forces 54 times greater than anything encountered during an Earth launch, and climbed through 30, 40, 50 kilometers of increasingly thinning but still punishing atmosphere. Your vehicle is battered. Its thermal protection has been pushed to its limits. Its structure has endured stresses no Earth rocket was ever designed to handle. But it's still functioning, still climbing. And now, somewhere around 48 to 50 kilometers above the surface, you enter a new region, the clouds of Venus. And if you've been paying attention to popular science articles or optimistic proposals about Venus exploration, you might think this is where things get better. You might think the clouds are the good part, the safe zone, the refuge. You would be wrong. The idea that Venus's clouds represent some kind of habitable zone has gained surprising traction in recent years, and it's easy to see why. The numbers seem encouraging at first glance. At an altitude of about 50 to 55 kilometers above Venus's surface, the temperature drops to a range between roughly 0 and 75 degrees Celsius. At around 55 kilometers, the temperature is approximately 20 to 30 degrees Celsius, close to a pleasant day on Earth. The atmospheric pressure at this altitude is about half an atmosphere to 1 atmosphere, remarkably similar to conditions at Earth's surface, or perhaps on a mountain. If you just looked at temperature and pressure alone, this thin band of Venus's atmosphere seems almost Earth-like. Some scientists have even proposed that floating habitats, essentially blimps or balloon stations, could operate at this altitude, taking advantage of the moderate conditions. The concept has appeared in NASA studies, in popular science magazines, and in countless YouTube videos describing Venus as a potential destination for human exploration. The clouds, the story goes, are where we could live. But this narrative is dangerously incomplete. It focuses on 2 variables, temperature and pressure, while ignoring a third that changes everything: chemistry. Because the clouds of Venus are not made of water. They're not fluffy white collections of ice crystals and water droplets like the clouds you see on Earth. The clouds of Venus are made of sulfuric acid, concentrated sulfuric acid. And when I say concentrated, I don't mean the dilute solutions you might encounter in a chemistry classroom. The sulfuric acid droplets in Venus's clouds have concentrations estimated between 75 and 98%. On Earth, concentrated sulfuric acid of this strength is one of the most dangerous chemicals in common industrial use. It is violently corrosive. It destroys organic material on contact. It attacks most metals. It reacts exothermically with water, meaning it generates intense heat when it contacts moisture. Getting a single drop of 98% sulfuric acid on your skin will cause an immediate chemical burn that destroys tissue. A splash across a larger area can cause injuries requiring hospitalization. And on Venus, this substance doesn't exist as a few drops in a laboratory. It exists as an entire cloud layer that stretches around the entire planet, spanning from about 48 kilometers to roughly 70 kilometers in altitude. That's a band of clouds approximately 20 to 22 kilometers thick, encircling the entire world, composed of droplets of one of the most corrosive substances known to chemistry. Let me describe the structure of these clouds in more detail because their layered nature matters for understanding why they're such an effective part of Venus's trap. The cloud system on Venus is typically divided into 3 main layers. The lower cloud layer extends from about 48 to roughly 52 kilometers altitude. The middle cloud layer spans from about 52 to 57 kilometers. The upper cloud layer reaches from approximately 57 to 70 kilometers. Below the lower cloud layer, from about 31 to 48 kilometers, there's a region of haze that contains smaller sulfuric acid particles and other aerosols. Above the upper cloud layer, there's another haze region extending to about 90 kilometers. Each layer has different characteristics. The lower cloud layer contains the largest droplets, some reaching diameters of several micrometers. These larger droplets are denser and create a thicker, more opaque layer. The middle cloud layer contains a mix of droplet sizes. The upper cloud layer contains smaller droplets and is somewhat thinner. But all 3 layers share the same basic composition: sulfuric acid and water, with sulfuric acid dominating. The sulfuric acid in Venus's clouds forms through a chain of chemical reactions driven by sunlight and volcanic activity. Venus has an atmosphere rich in sulfur dioxide, a gas produced by volcanic eruptions. Sulfur dioxide rises into the upper atmosphere where ultraviolet radiation from the sun breaks it apart and recombines it with water vapor and oxygen to form sulfuric acid. This sulfuric acid condenses into droplets, forming the cloud layers. The droplets grow, get heavier, and eventually fall. As they descend below about 48 kilometers, the increase in temperature evaporates them. The sulfuric acid breaks back down into sulfur dioxide and water vapor, which rise again and repeat the cycle. It's a continuous chemical cycle, a closed loop of creation and destruction that maintains the cloud layers permanently. This means the clouds are not a static feature. They're a dynamic chemical factory, constantly producing and recycling sulfuric acid. The entire cloud deck is active, reactive, and aggressive. Any material passing through this layer is being continuously exposed to fresh sulfuric acid droplets. Now, let's talk about what concentrated sulfuric acid actually does to materials, because this is where the cloud layer transforms from an abstract chemical curiosity into a practical engineering nightmare. Sulfuric acid at concentrations above 90% is an extraordinarily aggressive chemical agent. It attacks most metals through a combination of acid corrosion and oxidation. Carbon steel dissolves readily in concentrated sulfuric acid. Aluminum reacts violently with it. Copper, zinc, and tin are all corroded. Even metals that resist many other acids can be vulnerable to hot concentrated sulfuric acid. Titanium, which was used in the Venera lander pressure vessels, resists sulfuric acid at room temperature, but becomes increasingly vulnerable as temperatures rise. At the temperatures found in Venus's lower cloud layer, around 100 to 200 degrees Celsius, concentrated sulfuric acid becomes even more reactive than it is at room temperature. The combination of high concentration and elevated temperature makes it one of the most chemically hostile environments imaginable for engineering materials. There are materials that resist sulfuric acid. Certain ceramics, some specialized alloys, specific polymers like polytetrafluoroethylene, and glass can withstand concentrated sulfuric acid under certain conditions. But each of these has limitations. Ceramics are brittle and can crack under thermal shock or mechanical stress, both of which are abundant during a rocket ascent through a turbulent atmosphere. Specialized alloys are heavy. Polymers degrade at higher temperatures. Glass is fragile. There is no perfect material that is simultaneously lightweight, strong, thermally resistant, and immune to sulfuric acid. Any material choice involves compromise, and every compromise introduces a vulnerability. For a vehicle ascending through Venus's cloud layers, sulfuric acid exposure isn't a brief encounter. The cloud deck is 22 kilometers thick. A vehicle climbing at a few hundred meters per second would spend multiple minutes passing through the clouds. During this time, concentrated sulfuric acid droplets would be impacting the vehicle's surface continuously. At the speeds involved in a rocket ascent, these droplets wouldn't just settle gently on the surface. They would strike with kinetic energy, splashing and spreading across whatever surface they hit. The vehicle would be flying through a rain of acid, with droplets hitting every exposed surface. This creates a specific kind of damage that's different from static immersion in acid. When acid droplets impact a surface at high speed, they can penetrate protective coatings, find gaps in seals, and reach underlying materials that aren't acid resistant. Joints between panels, edges of heat shields, interfaces between different materials. All of these are potential weak points where acid can infiltrate and attack the underlying structure. Any crack, scratch, or imperfection in a protective coating becomes a point of entry for corrosion. And remember, this vehicle has already been through a tremendous ordeal. It sat on Venus's surface at 465 degrees Celsius and 92 atmospheres. It endured enormous thermal stresses during that time. Then it fired its engines and pushed through the densest, hottest part of the atmosphere, experiencing massive aerodynamic loads and continued thermal assault. By the time it reaches the cloud layer, its surface is not pristine. It's been thermally cycled, mechanically stressed, and possibly already slightly damaged. Any protective coatings have been tested to their limits, and now, in this compromised state, the vehicle enters a 22-kilometer thick bath of concentrated sulfuric acid. The corrosion isn't just a surface phenomenon. Sulfuric acid can attack seals around engine nozzles, sensor windows, communication antennas, and any other component that needs to be exposed to the outside environment. A rocket engine nozzle, by definition, must be open to the atmosphere. Hot acid droplets entering the nozzle could corrode internal components, degrade the nozzle's performance, or clog smaller openings. Sensor windows used for navigation or guidance could become etched or opaque as acid attacks the glass or transparent material. Communication antennas could corrode, degrading the vehicle's ability to transmit data or receive commands. But sulfuric acid isn't the only chemical hazard in Venus's clouds. The atmosphere surrounding the clouds contains other reactive species. Sulfur dioxide is present in significant concentrations throughout the cloud region. Sulfur dioxide is itself corrosive and toxic. It reacts with water to form sulfurous acid, another corrosive compound. Below the cloud layer, there's evidence of other sulfur compounds, including hydrogen sulfide and carbonyl sulfide, both of which are reactive and toxic. Some researchers have also detected phosphine in Venus's atmosphere, though this finding remains controversial. The chemical environment in and around the clouds is complex and aggressive, a cocktail of reactive sulfur compounds that attack materials through multiple chemical pathways simultaneously. There's also the question of electrical activity. Multiple observations, including data from the Soviet Venera missions and the European Space Agency's Venus Express orbiter, have detected what appear to be lightning discharges in Venus's atmosphere, particularly in and around the cloud layers. The evidence is debated. Some scientists argue the signals could have other explanations. But if lightning does occur in Venus's clouds, it adds another hazard for an ascending vehicle. A lightning strike on a vehicle that's already thermally stressed, structurally compromised, and coated in conductive sulfuric acid could cause catastrophic electrical damage. On Earth, aircraft are struck by lightning relatively frequently and usually survive because they're designed for it. But a Venus ascent vehicle would be in a far more vulnerable state, and the consequences of an electrical system failure during powered ascent would be fatal to the mission. Now, let's talk about the winds, because the cloud layer is also where Venus's atmospheric dynamics become most extreme. I mentioned earlier that Venus's atmosphere exhibits superrotation. The entire atmosphere rotates much faster than the planet itself. At the cloud tops, around 65 to 70 kilometers altitude, wind speeds reach approximately 360 kilometers per hour. That's roughly 100 meters per second. These winds circle the planet in about 4 Earth days, while the solid planet beneath takes 243 Earth days to complete a single rotation. The atmosphere is moving 60 times faster than the surface. For a vehicle ascending through the clouds, these winds create several problems. First, there's the absolute wind speed. At 360 kilometers per hour, the winds are equivalent to a Category 5 hurricane on Earth, the most intense category of tropical cyclone. A sustained Category 5 hurricane on Earth has winds exceeding 252 kilometers per hour and can flatten buildings, uproot trees, and destroy virtually anything in its path. The winds at Venus's cloud tops exceed this, and unlike a hurricane on Earth, which is a localized storm that you can fly around, the winds on Venus encircle the entire planet. There is no calm region. There is no eye of the storm to aim for. The winds are everywhere at this altitude, all the time. Second, there are the wind shears. Wind speed changes with altitude in the cloud region. Near the bottom of the clouds, winds are slower, perhaps 40 to 60 kilometers per hour. By the cloud tops, they've accelerated to over 360 kilometers per hour. This means that as your vehicle climbs through the clouds, the wind speed it encounters changes continuously. These changes in wind speed with altitude, called vertical wind shear, create forces on the vehicle that change with time. The guidance system must constantly adjust to compensate for shifting crosswinds. If the vehicle is ascending roughly vertically, these winds push it sideways. If it's ascending at an angle, the winds affect its trajectory in complex ways that depend on the vehicle's orientation, speed, and altitude. Third, there's turbulence. The cloud layers of Venus are not smooth, laminar flows, they're turbulent. Convective cells, similar to thunderstorm cells on Earth, but operating in a sulfuric acid cloud system, create updrafts, downdrafts, and chaotic eddies. Data from the Vega balloon missions in 1985, which deployed balloons that floated in Venus's cloud layer for about 46 hours, showed significant vertical motions. The balloons were carried up and down by convective currents, sometimes rising or falling by a kilometer or more. For a vehicle trying to ascend on a controlled trajectory, these convective motions add unpredictable forces. A strong downdraft could slow the vehicle's ascent or push it back down into the denser, hotter regions it just climbed out of. An updraft in the wrong direction could push it off course. Turbulence creates structural loads that are difficult to predict and design for because they're essentially random. The Vega balloon data also revealed something else interesting and troubling. The cloud layer is not uniform. There are regions of varying density with thicker and thinner patches. Some areas have more sulfuric acid content than others. The horizontal variations mean that a vehicle ascending through the clouds might encounter pockets of especially dense acid concentration, interspersed with slightly clearer regions. This variability makes it impossible to predict exactly what chemical exposure the vehicle will face at any given point. You can design for average conditions, but averages don't tell you about the worst case. And in engineering, especially in a situation where you get one chance and no rescue is possible, you have to design for the worst case. Let me address the floating habitat concept directly, because it's relevant to understanding why the clouds are not a refuge. The idea of a floating station at 50 to 55 kilometers altitude has genuine scientific basis. At that altitude, a balloon filled with breathable Earth air would actually float in Venus's carbon dioxide atmosphere because our air is less dense than carbon dioxide at the same temperature and pressure. The temperature and pressure at this altitude are close to Earth-like. From a purely physical standpoint, a floating platform could theoretically remain aloft at this altitude indefinitely, held up by buoyancy without needing any fuel or power for lift. But here's what the popular accounts usually gloss over. That floating platform would be immersed in sulfuric acid clouds. The exterior of the structure would be in constant contact with concentrated sulfuric acid droplets. Every seal, every joint, every surface would be under continuous chemical attack. The structure would need to be made of acid-resistant materials that can maintain their integrity indefinitely. On Earth, industrial facilities that handle concentrated sulfuric acid require constant maintenance and regular replacement of components that corrode over time. A floating station on Venus would have no supply chain, no replacement parts, no maintenance crews with access to fresh materials. Everything the station needs to survive the acid environment would have to be brought along and would have to last as long as the mission. And the acid doesn't just attack the outside, it creates a contamination risk for anything that needs to interface between the interior and the exterior. Airlocks, sample collection ports, communication antennas, solar panels, all of these need some exposure to the outside environment. Every point of exposure is a point where acid can infiltrate. Sulfuric acid is also hygroscopic. It absorbs water aggressively. If any moisture from inside the habitat leaked to the exterior, the acid would absorb it, potentially creating hotspots of corrosion where the acid becomes more dilute and paradoxically more reactive to certain metals. Dilute sulfuric acid is actually more corrosive to many metals than concentrated acid because concentrated acid forms a passive protective layer on some metal surfaces that dilute acid doesn't. The floating habitat concept also faces the wind problem. At 55 kilometers altitude, the winds are moving at roughly 200 kilometers per hour relative to the surface. A floating station would be carried along with these winds, circling the planet every few days. This isn't inherently a problem. A station moving with the wind doesn't experience the wind as a force because it's traveling at the same speed as the surrounding air. But it does mean the station has no fixed position. It circles the planet continuously. Maintaining communication with Earth would require either multiple ground antennas or a relay satellite, both of which add mission complexity. And if the station needed to hold a specific position, for example, to stay over a particular surface feature for observation, it would need to fight winds of 200 kilometers per hour continuously. That would require enormous amounts of energy. None of this means a floating mission is impossible, but it means the clouds are far from a comfortable refuge. They're a slightly less immediately lethal layer of a fundamentally hostile planet. The temperature and pressure are survivable. The chemistry is not. And for a vehicle trying to ascend through the clouds, rather than float in them, the chemistry is encountered as a gauntlet to be run, not a place to rest. Let me also address the optical environment in the clouds, because it matters for navigation. Venus's cloud layer is optically thick. Very little sunlight penetrates to the lower clouds. The upper clouds reflect about 75% of incoming sunlight back into space, which is why Venus appears so bright from Earth and why the surface stays relatively dim despite Venus being closer to the Sun than Earth is. Inside the cloud layer, visibility is severely limited. Light is scattered in all directions by the sulfuric acid droplets. An ascending vehicle would be flying essentially blind through the clouds, unable to use visual references for navigation. It would need to rely entirely on inertial guidance, radar, or other instruments that don't require clear sight lines. On Earth, rockets launch through clouds all the time, but Earth's clouds are made of water, which doesn't corrode anything, and Earth's clouds are typically only a few kilometers thick at most. The period of reduced visibility is brief. On Venus, the cloud layer is 22 kilometers thick. An ascending vehicle would be in reduced visibility conditions for a substantial portion of its climb, far longer than any Earth rocket experiences. There's one more factor about the clouds that deserves attention, and it concerns what lies at the boundary between the cloud layer and the region above. The vehicle exits the top of the cloud layer at around 70 kilometers altitude. It enters the upper haze region. Here, the sulfuric acid droplets are smaller and less dense, but they're still present. The atmosphere is much thinner at this altitude, with pressure down to a few hundredths of an atmosphere. The temperature has dropped significantly to roughly -40 to -50 degrees Celsius at the cloud tops. This is actually colder than the vehicle has experienced at any point during its ascent. The vehicle went from 465 degrees Celsius at the surface, through gradually decreasing temperatures during the atmospheric climb, through the moderate temperatures of the mid-cloud region, and now into sub-zero temperatures above the clouds. This temperature reversal creates a thermal shock problem. Materials that have been heated to extreme temperatures and then gradually cooled during the ascent are now being rapidly cooled further as they emerge above the clouds into the cold upper atmosphere. Thermal shock, the stress created by rapid temperature changes, can crack ceramics, delaminate composite materials, and cause metal fatigue. A vehicle that survived the heat of the surface and the acid of the clouds might suffer structural failures from the rapid cooling above the clouds. Engineers call this thermal cycling, and it's one of the most destructive forces that materials can experience. Venus puts a vehicle through an extreme thermal cycle during ascent. From extremely hot at the surface, through a long period of gradually decreasing but still elevated temperatures, through moderate temperatures in the clouds, and then into cold temperatures above them. Each transition stresses the materials differently, and the cumulative effect can be devastating. So let me synthesize what the cloud layer really represents for a vehicle trying to escape Venus. It is not a safe zone. It is not a refuge. It is the third layer of the trap. And in many ways, it's the most insidious layer because it looks survivable. The temperature and pressure at cloud altitude are close to Earth-like. If you could somehow ignore the chemistry, the winds, the turbulence, and the visibility, it would seem almost pleasant compared to the hellscape of the surface and the crushing lower atmosphere. But you can't ignore those things. The sulfuric acid is real. The corrosion is real. The winds are real. The turbulence is real. The darkness inside the cloud layer is real. And the thermal shock at the top of the clouds is real. The clouds are a trap within a trap. They're the part of Venus that looks like it might be on your side, but isn't. They're the part that popular science describes as potentially habitable, while glossing over the fact that habitable temperatures and pressures mean nothing if the air itself is eating your vehicle. The surface traps you with heat and pressure. The lower atmosphere traps you with density and drag. The clouds trap you with acid and wind and turbulence and the false promise of safety. Each layer of Venus's atmosphere presents a different kind of obstacle, and together they form a defense in depth that no single engineering solution can overcome easily. A vehicle that has somehow survived all three layers: the surface, the dense lower atmosphere, and the corrosive cloud deck, emerges above the clouds battered, depleted, and facing one final challenge. The challenge that matters most: it still has to reach space. It still has to accelerate to orbital velocity or escape velocity. It still has to break free of Venus's gravity entirely. And after everything it's been through, after burning enormous quantities of fuel just to get through the atmosphere, after enduring thermal stresses that would destroy most spacecraft, after being bathed in concentrated sulfuric acid for an extended passage through the clouds, this vehicle now has to perform the most energy-intensive part of the entire mission with whatever fuel and structural integrity it has left. The clouds aren't the end of the escape. They're the last barrier before the real test begins. And what comes next is arguably the most daunting physics problem in all of planetary exploration. Your vehicle has emerged above the clouds, 70 kilometers above the surface of Venus, battered and depleted, stripped of most of its fuel, its protective coatings etched by sulfuric acid, its structure fatigued by thermal cycling that took it from 465 degrees Celsius to -50 in the span of a single ascent. The atmosphere up here is thin. The pressure is down to a few hundredths of an atmosphere. The density is low enough that drag is no longer the dominant problem. For the first time since leaving the surface, your vehicle is in something that resembles the conditions an Earth rocket would consider normal for the upper stages of flight. But here is where the final and perhaps most unforgiving layer of Venus's trap reveals itself. Because now you need speed, enormous speed. And you need it with a vehicle that has already spent most of its energy just getting to this point. To understand why this final stage is so difficult, you need to understand what it actually means to escape from a planet. When we talk about escaping a planet's gravity, we're talking about achieving a specific velocity, not altitude, velocity. Getting high above a planet is not the same as escaping it. You could be 1,000 kilometers above Venus, and if you're not moving fast enough horizontally, you'll fall right back down. What keeps a spacecraft in orbit isn't height, it's speed. Orbital velocity is the speed at which a spacecraft moves sideways, fast enough that as it falls toward the planet due to gravity, the planet's surface curves away beneath it at the same rate. The spacecraft is perpetually falling, but never hitting the ground, because the ground keeps curving away. This is what an orbit is: a continuous state of falling around a planet rather than falling into it. For Venus, the orbital velocity at low orbit, roughly 300 kilometers above the surface, is about 7.2 kilometers per second. That's approximately 25,900 kilometers per hour. To put that in human terms, that's about 33 times the speed of sound at sea level on Earth. It's fast enough to cross the entire continental United States in about 6 minutes. Any vehicle that wants to orbit Venus needs to reach this speed. And any vehicle that wants to leave Venus entirely, to escape its gravity and travel to another planet or back to Earth, needs to go even faster. The escape velocity from Venus's surface is about 10.4 kilometers per second. From a 300 kilometer orbit, escape velocity is somewhat lower, around 9.2 kilometers per second, because you're farther from the planet's center of mass, and gravity is slightly weaker. But either way, these are enormous velocities that require tremendous amounts of energy to achieve. Now here's the critical comparison. Venus's escape velocity of 10.4 kilometers per second is remarkably close to Earth's escape velocity of 11.2 kilometers per second. The two planets have similar masses and similar radii, so their gravitational pulls are similar. From a pure gravity standpoint, escaping Venus is almost as hard as escaping Earth. And escaping Earth is already one of the hardest things humanity has ever done. Think about what it takes to launch something from Earth. The Saturn V rocket that sent Apollo astronauts to the moon stood 110 meters tall and weighed about 2,970 metric tons at launch. Roughly 85% of that mass was fuel. The remaining 15% was engines, structure, and the relatively tiny payload. Building a Saturn V required the combined efforts of over 300,000 engineers, technicians, and scientists working across thousands of companies and facilities. The launch complex at Kennedy Space Center was one of the most sophisticated pieces of infrastructure ever constructed, with flame trenches, water suppression systems, fuel handling facilities, clean rooms, and tracking stations. Months of preparation went into each launch. Teams of engineers monitored every system, checked every connection, verified every calculation, and even with all of that support, with the full industrial might of the United States behind it, launches sometimes failed. Rockets exploded on the pad, broke apart during ascent, or experienced system failures that ended missions. Now, consider what a Venus ascent vehicle would have. No launch complex, no ground crew, no months of preparation, no ability to inspect the vehicle before launch, no ability to fix problems discovered at the last minute, no flame trench to direct exhaust, no water suppression system to protect the pad, no pad at all, really, just whatever patch of volcanic rock the lander happened to set down on. The vehicle has been sitting in an environment that would destroy most industrial equipment within hours. Its components have been slowly degrading since the moment it landed. No engineer has looked at it. No technician has verified that every seal is intact and every connection is solid. It simply has to work. First try, perfectly, in the most hostile environment in the inner solar system. And it has to achieve nearly the same velocity that required the Saturn V and 300,000 people and billions of dollars and years of preparation to achieve on Earth. The absurdity of that comparison is hard to overstate. And the Saturn V was designed to operate in Earth's relatively benign conditions. Room temperature at the launch pad, 1 atmosphere of pressure, a thin atmosphere that the rocket punches through in about 2 minutes. No sulfuric acid, no supercritical carbon dioxide, no 465-degree surface temperatures. On Venus, you need to achieve nearly the same velocity, against nearly the same gravity, but after your vehicle has already expended an enormous fraction of its fuel just climbing through the atmosphere. This is the fundamental problem. On Earth, a rocket starts its ascent with a full load of fuel. It uses some of that fuel to climb through the atmosphere, typically losing about 0.3 to 0.5 kilometers per second of delta V to atmospheric drag. That's a relatively small tax on the total energy budget. The vast majority of the fuel goes toward building up horizontal velocity to reach orbit. On Venus, the atmospheric drag losses are not a small tax. They're a crushing burden. Estimates vary depending on vehicle design and trajectory, but the additional delta V required to push through Venus's atmosphere compared to an equivalent ascent in vacuum could be 2 to 3 kilometers per second or more. That might not sound like much compared to the total delta V budget of 10 or 11 kilometers per second. But because of the exponential nature of the rocket equation, even small additions to the required delta V translate into enormous increases in the amount of fuel needed. Let me explain the rocket equation in a way that makes this concrete. The Tsiolkovsky rocket equation, named after the Russian scientist Konstantin Tsiolkovsky, who derived it in 1903, describes the fundamental relationship between a rocket's velocity change, the velocity of its exhaust, and the ratio of its initial mass to its final mass. The equation is elegant but merciless. It says that to double your delta V, you don't need to double your fuel. You need to square your fuel ratio. The relationship is exponential, not linear. If a rocket needs a mass ratio of 3:1, meaning the fully fueled rocket is 3 times heavier than the empty rocket, to achieve a certain delta V, then doubling the delta V requires a mass ratio of 9:1. Tripling it requires 27:1. The numbers escalate with terrifying speed. On Earth, the total delta V to reach low orbit is about 9.4 kilometers per second. Using a high-performance liquid rocket engine with an exhaust velocity of about 3.5 kilometers per second, the required mass ratio works out to roughly 15:1. This means a rocket headed for low Earth orbit needs to be about 15 times heavier when fully fueled than it is when empty. For every kilogram of payload and structure you want to put in orbit, you need about 14 kilograms of fuel. This is already an extremely challenging ratio. It's why rockets are built so lightly, why they use the thinnest possible tank walls, why every gram of unnecessary weight is eliminated. There's almost no margin. On Venus, with an estimated total delta V of 11 to 12 kilometers per second, accounting for the higher drag losses, the required mass ratio climbs to somewhere between 25:1 and 30:1 or worse, depending on the engine performance achievable in Venus conditions. For every kilogram of payload, you need 25 to 30 kilograms of fuel, and that fuel has to survive the surface conditions of Venus. It has to remain stable at 465 degrees Celsius. It has to be stored in tanks that can withstand 92 atmospheres of external pressure and the thermal stresses of ascent. The tanks themselves have to be heavier than Earth rocket tanks, because they need to handle these extreme conditions. Heavier tanks mean more structural mass. More structural mass means the payload fraction gets even smaller. The mass ratio gets even worse. You need even more fuel to lift the heavier tanks, which makes the vehicle heavier, which requires more fuel. The spiral tightens with every additional engineering constraint Venus imposes. Let me make this tangible with a thought experiment. Imagine you want to launch a payload of 100 kilograms from Venus's surface to low Venus orbit. Just 100 kilograms. That's roughly the mass of a large adult human, or a small satellite, or a collection of rock samples. On Earth, putting 100 kilograms into low orbit requires a launch vehicle weighing roughly 1,500 to 2,000 kilograms at liftoff, depending on the rocket's efficiency. That's achievable. We have sounding rockets and small orbital launch vehicles in that size class. On Venus, with a mass ratio of 25:1 or worse, the same 100 kilogram payload would require a launch vehicle weighing at least 2,500 kilograms. Probably much more when you account for the heavier structures needed to survive Venus conditions. And the 2,500 kilograms or more has to be delivered to Venus's surface intact, survive the landing, survive the surface conditions, and then perform a flawless launch sequence in an environment that destroys spacecraft in under 2 hours. Now consider what delivering that vehicle to Venus's surface requires. You first have to launch it from Earth, which means it has to fit inside or on top of an Earth launch vehicle. Then you have to send it on a trajectory to Venus, which takes several months. Then you have to decelerate it and guide it through Venus's atmosphere to a landing, which requires heat shields and parachutes or retro rockets. The landing system adds mass. The interplanetary cruise stage adds mass. The Earth launch vehicle has to be sized to lift all of this. A mission to launch 100 kilograms from Venus's surface back to orbit might require an Earth launch vehicle weighing tens of thousands of kilograms or more. The logistics cascade outward at every level. This is why no space agency has ever attempted to launch anything from Venus's surface. It's not that the idea hasn't been considered. It has, extensively. NASA, the European Space Agency, and others have studied Venus sample return missions as conceptual exercises. The goal would be to land on Venus, collect a sample of surface material, launch that sample back into Venus orbit, rendezvous with an orbiter, and return the sample to Earth for analysis. Such a mission is considered one of the holy grails of planetary science, because Venus surface samples would reveal enormous amounts about the planet's geological history and the evolution of its atmosphere. But every study has concluded that a Venus sample return mission would be among the most technically challenging missions ever attempted. The engineering problems are staggering. You need a lander that can survive the surface long enough to collect a sample. You need an ascent vehicle small enough to be carried by the lander, but powerful enough to reach orbit from the surface. You need that ascent vehicle to function after exposure to Venus's surface conditions. You need an orbiter waiting in Venus orbit to receive the sample and bring it home. Every component must work perfectly, autonomously, with no possibility of repair or intervention. The total mission would likely cost billions of dollars and take decades to develop. And even then, the risk of failure would be enormous, because the surface conditions leave essentially zero margin for error. Some mission concepts try to simplify the problem by not launching from the surface at all. One approach is to use a balloon or atmospheric probe that collects a sample of the atmosphere or cloud particles rather than surface material. The probe would float at altitude, collect its sample, and then launch a small rocket from the relative safety of the upper atmosphere. Launching from 50 or 60 kilometers altitude avoids the worst of the surface conditions. The pressure and temperature are much lower. The atmospheric density is manageable. The delta V requirements are reduced because you're starting from a higher altitude with less atmosphere above you. But even this simplified approach has challenges. You still need to get the balloon probe to Venus and deploy it successfully. The probe has to survive in the sulfuric acid cloud layer long enough to collect a meaningful sample. The ascent rocket has to be carried aloft by the balloon, adding mass to the balloon system. And the rocket still needs to achieve orbital velocity from 50 or 60 kilometers altitude, which, while easier than launching from the surface, is still a substantial engineering challenge. The atmosphere above 50 kilometers, though much thinner than below, still creates some drag. The wind speeds at this altitude are significant, and the rocket has to function after being immersed in a sulfuric acid environment during the balloon's float period. Another proposed approach avoids the ascent problem entirely. Instead of launching a sample back to orbit, You design the lander to perform all its analysis on the surface and simply transmit the data back to an orbiter via radio. This eliminates the need for an ascent vehicle altogether. The Venera landers took this approach, analyzing soil samples on the surface and sending the data back before they were destroyed. Modern instruments could potentially do much more sophisticated analysis. But this approach has its own limitations. No matter how good your onboard instruments are, they can't replicate the full range of analyses that could be performed in a laboratory on Earth. Some measurements require equipment too large or too delicate to send to Venus. And the limited survival time on the surface means you can only collect and analyze a finite number of samples before your instruments die. A returned sample that could be studied in Earth laboratories for decades would be scientifically invaluable in ways that onboard analysis simply cannot match. There is one more approach that has been discussed, and it illustrates just how desperate the engineering constraints make the situation. Some researchers have proposed using a completely passive ascent system. Instead of a rocket, you would use a buoyant vehicle, essentially a balloon, to float the sample up through the atmosphere. A sealed container filled with a gas less dense than carbon dioxide, such as helium or even breathable air, would rise through Venus's atmosphere like a helium balloon rises through Earth's atmosphere. Since Venus's atmosphere is almost entirely carbon dioxide, which is heavier than many common gases, buoyancy could theoretically carry a small payload from the surface all the way up to the cloud layer or higher, without any fuel expenditure at all. This concept has some appeal. It avoids the fuel problem entirely for the atmospheric ascent phase. A buoyant vehicle doesn't need engines or propellant to climb through the atmosphere. It just rises because it's lighter than its surroundings. But there are serious practical problems. First, the buoyant vehicle would rise slowly. A balloon on Venus's surface would accelerate upward, but the ascent through the dense lower atmosphere would take time, possibly hours. During this time, the vehicle and its sample are being cooked by the ambient temperature. At the surface, that's 465 degrees Celsius. The balloon material has to survive this temperature. The sample container has to survive it. The gas inside the balloon must remain contained despite the extreme heat, which increases gas pressure inside the balloon and stresses the envelope material. Even as the balloon rises and the temperature decreases, conditions remain extremely hot for tens of kilometers. Second, even if the balloon successfully carries the sample up to the cloud layer, you still need to get it from there into orbit. Buoyancy can get you to 50 or 60 kilometers altitude, where the atmosphere thins enough that the balloon stops rising. But from there, you still need a rocket to accelerate the sample to orbital velocity. The balloon doesn't solve the orbital insertion problem. It just moves the starting point from the surface to the clouds. This helps enormously with the delta V budget because you've eliminated the worst part of the atmospheric drag, but it doesn't eliminate the need for a rocket entirely. Third, the balloon concept introduces its own risks. A balloon ascending through Venus's atmosphere passes through the sulfuric acid cloud layer. The balloon envelope, whatever it's made of, has to resist concentrated sulfuric acid for the duration of the passage through the clouds. If the envelope develops a leak, the lifting gas escapes, and the balloon descends, back down into the heat, back down into the crushing pressure, back down to the surface, where it will be destroyed. There is no recovery from a balloon failure during ascent. The sample and the vehicle are lost. Let me step back now and think about what all of this means when you put every layer of the problem together. Venus is constructed through nothing more than the blind operation of physics and chemistry, a layered defense system against escape that is without parallel in our solar system. The surface layer is a furnace operating at 465 degrees Celsius and 92 atmospheres, hot enough to melt common metals and pressurized enough to crush most structures. The lower atmospheric layer is a wall of gas so dense it behaves like a fluid, creating drag forces 54 times greater than those encountered during an Earth rocket launch, requiring enormous fuel expenditure just to push through. The cloud layer is a 22-kilometer thick band of concentrated sulfuric acid, driven by hurricane-force winds and turbulence, attacking the chemical integrity of any vehicle that passes through it. And above all of this, the orbital mechanics layer demands that a vehicle achieve nearly the same velocity as it would need to escape Earth, using whatever fuel and structural integrity remains after surviving the 3 layers below. Each layer alone would be a formidable engineering challenge. Together, they create a problem that compounds at every stage. The surface destroys your vehicle while you prepare to launch. The lower atmosphere devours your fuel as you fight through it. The clouds corrode your structure as you pass through them. And the orbital mechanics demand performance from a vehicle that has been systematically degraded by everything it just endured. It is not any single factor that makes Venus inescapable. It is the combination of all of them, stacked one on top of the other, each one exploiting the damage done by the previous one. Consider the contrast with every other destination we've ever launched from or seriously plan to launch from. On Earth, we launch from benign surface conditions through a thin atmosphere and reach orbit routinely. It's hard, but it's a solved problem. We've done it thousands of times. On the Moon, we launch from vacuum with low gravity and no atmosphere at all. Apollo did it 6 times with 1960s technology. On Mars, the surface conditions are cold but not destructive. The atmosphere is thin enough to be almost negligible during ascent. The gravity is low. NASA has studied Mars sample return missions, and while they're complex and expensive, they're considered feasible with current or near-future technology. A Mars ascent vehicle is a relatively modest rocket that doesn't need to be particularly heat-resistant or acid-proof. It just needs to work in cold, thin air. Venus is different in kind, not just in degree. It's not a slightly harder version of an Earth launch or a Mars launch. It's a fundamentally different problem that requires fundamentally different solutions. Solutions that in many cases don't exist yet. We don't have materials that are simultaneously lightweight, structurally strong, thermally resistant to 465 degrees Celsius, and immune to concentrated sulfuric acid. We don't have rocket engines designed to operate at 92 atmospheres of ambient pressure. We don't have guidance electronics that can function reliably at Venus surface temperatures. We don't have thermal protection systems that can handle the full range of temperatures encountered during a Venus ascent, from 465 degrees Celsius at the bottom to -50 at the cloud tops. Each of these is an unsolved engineering problem, and a Venus ascent vehicle needs to solve all of them simultaneously. This is why Venus is, in a very real sense, a one-way destination. Everything we've ever sent there has been designed to go down, not come back up. The Venera landers, the Vega probes, even future proposed missions like Da Vinci are designed as descent probes, falling through the atmosphere, collecting data on the way down, and eventually being destroyed. We send things to Venus's surface the way you'd drop a sensor into a volcano. You get what data you can before the environment destroys the instrument, and you accept that the instrument is gone. The implications of this extend beyond just Venus itself. Venus teaches us something fundamental about what it means for a planet to be truly hostile. We often think of planetary habitability in terms of temperature and the presence of liquid water, but Venus shows us that a planet can be a prison even if you're not trying to live there, even if you're just trying to visit and leave. The combination of a dense atmosphere, extreme surface conditions, and corrosive chemistry creates a barrier that isn't just difficult to overcome. With current technology, it may be effectively impossible to overcome for anything larger than the most minimal payload. And this raises a haunting question. If Venus is this difficult for robotic spacecraft, built from the most advanced materials available to 21st century engineering, what would it mean for anything biological? Not for us. We would die on Venus's surface in seconds, protected or not. But what about the possibility of life in Venus's clouds? The idea that microbial organisms might exist floating in the cloud layers where temperatures and pressures are moderate. If such life exists, it would be permanently trapped. Not just on Venus, but within the cloud layer itself. Below the clouds, the temperature rises to levels that would destroy any conceivable biochemistry. Above the clouds, the atmosphere thins to near vacuum and temperatures drop far below freezing. The habitable band is perhaps 10 to 15 kilometers thick. Any life that evolved there would be confined to that narrow layer for its entire evolutionary history. It could never reach the surface. It could never reach space. It would be born, live, reproduce, and die within a thin shell of atmosphere, never knowing that anything existed beyond it. Think about what that kind of existence would mean. On Earth, life started in the oceans and eventually colonized the land, the air, the deep crust, the highest mountains, the polar ice caps. Life spread everywhere conditions allowed, and then adapted to push into places conditions didn't originally allow. Life on Earth is expansive. It reaches outward. It fills every available niche, and then creates new ones. Life in Venus's clouds would be the opposite. It would be fundamentally confined. There would be no land to colonize because the surface is a furnace. There would be no ocean to explore because the oceans boiled away billions of years ago. There would be no higher atmosphere to drift into because the temperatures above the clouds drop below what any water-based biochemistry could tolerate. The entire biosphere, if it exists at all, would be a thin floating layer of microbes suspended in sulfuric acid droplets, cycling endlessly through the cloud layers as convective currents carry them up and down within that narrow habitable band. They would rise until the air became too cold and thin, then sink until the heat became too intense, then rise again. An eternal cycle within a prison of altitude. No evolution toward complexity could change this. No adaptation could break through the thermal barriers above and below. The cleverest, most resilient organism Venus could ever produce would still be confined to that same thin shell of survivable atmosphere, forever circling a planet it could never truly inhabit. Venus wouldn't just trap a spacecraft, it would trap life itself, limiting it to the smallest possible cage that physics allows. This is the deepest lesson Venus has to teach us. A planet doesn't need walls or fences or guards to be a prison. It doesn't need intelligence or intent. It just needs physics. The right combination of gravity, atmospheric density, temperature, pressure, and chemistry can create a trap so thorough that nothing, not a spacecraft, not a message, not even a living organism, can escape. Venus has all of these in exactly the wrong combination. Its gravity is strong enough to hold a thick atmosphere. Its atmosphere is thick enough to create crushing pressure and extreme greenhouse heating. Its chemistry has filled that atmosphere with corrosive compounds. Its temperature is high enough to destroy most materials, and its orbital mechanics demand enormous velocity to break free. Every layer reinforces every other layer. The thick atmosphere causes the greenhouse heating. The greenhouse heating maintains the high temperature. The high temperature keeps the atmosphere puffed up and dense. The dense atmosphere creates massive drag. The massive drag demands more fuel. More fuel means a larger vehicle. A larger vehicle means more surface area exposed to heat, pressure, and acid. More exposure means faster degradation. Faster degradation means less time to complete the ascent. Less time means you need to go faster. Going faster through dense atmosphere means even more drag. The system is self-reinforcing. Every aspect of Venus's hostility feeds back into every other aspect, creating a web of interlocking constraints that tighten around any attempt to escape. In all of planetary science, in all of our exploration of the solar system, there is no other world that combines these factors so completely. Mercury is hot but has no atmosphere to trap you. Mars is cold and hostile but has thin air and weak gravity that make departure straightforward. The gas giants have deep atmospheres, but their incredible sizes place them in a different category of challenge entirely. Among the rocky terrestrial worlds, the worlds most similar to Earth, Venus stands alone as a place where arrival means permanence, where descent is a commitment, where the ground, the air, the clouds, and the sky all conspire through nothing but the impersonal operation of natural law to ensure that whatever comes down does not go back up. The next time you look at Venus in the evening or morning sky, that brilliant point of light outshining everything except the moon, remember what lies beneath those bright reflective clouds. Remember that the beauty you see, that dazzling whiteness, is sunlight bouncing off a planet-wide layer of sulfuric acid. Remember that beneath those clouds lies an atmosphere so dense and so hot that it has crushed and melted every machine humanity has ever sent there. Remember that the surface of that gleaming world is a furnace operating at temperatures that would liquefy metal, pressures that would crush a submarine, and chemistry that would dissolve the wreckage afterward. And remember that all of this, the heat, the pressure, the density, the acid, the wind, the drag, the orbital mechanics, works together as a single interlocking system. Not designed, not intentional, just physics, just chemistry, just a planet being what it is. But the result is the same as if it were designed. Venus is a trap. A beautiful, brilliant, gleaming trap hanging in the sky. And if you ever went down to its surface, it would never let you leave. Not because it wants to keep you. A planet doesn't want anything. But because every law of physics that operates there, every chemical reaction, every atmospheric dynamic, every thermodynamic principle, all of them point in the same direction. Down, inward, deeper, hotter, and none of them, not a single one, will help you go back up. That is why Venus doesn't let you escape. Not because of any one thing, not the heat alone, not the pressure alone, not the acid alone, not the drag alone, not the gravity alone, but because all of them together, layered one on top of the other, each magnifying the others, each exploiting the weaknesses created by the others. form a planetary defense so complete that 4 decades after our last landing, with all the technological advancement humanity has achieved since then, we still have no proven way to bring anything back. The surface of Venus remains the only place in the inner solar system where arrival and destruction are essentially the same event. Where landing means dying. Where going down means staying down. Where a planet that looks like Earth's twin from a distance reveals itself up close to be something far more alien and far more dangerous than almost any other world we know. Venus is Earth's size. Venus is Earth's neighbor. But Venus is no one's home. And for anything that touches its surface, Venus is a place from which there is, as yet, no return.